This conference will now be recorded.
Hello, today we're going to talk about assessing potential effects of climate change on highway runoff flows and loads in southern New England by using a planning level space for time analysis. This study was prepared in cooperation with the Federal Highway Administration, and it was first presented at the Transportation Research Board 102nd Annual Meeting in Washington, D.C. We've held off on this webinar to give the Transportation Research Record time to publish it. So currently, the paper is available as an online paper until it's formally published in the Transportation Research Record as an open access article. So if you use this web address, which we will show again later, you can get to the paper, and we paid the publishing fee so that everyone can access and download the paper. So we did this study because Federal Highway is planning for resilience to climate change. They've done a lot on precipitation changes, flood flow changes, potential effects on infrastructure, but they have not yet done a lot of stormwater quality research, so more information was needed. So here we have a map of the United States that shows available USGS stream gauges and the record length in years. So what we can see from this map is that long-term data needed to assess potential effects of climate change on flood flows are available at about 13,000 USGS stream gauges nationwide. So for flood flows, we have a lot of available data that we can analyze, and stream flow data is collected on, it's reported on a daily basis, and some stations have more than 100 years of record. In comparison, the highway runoff database has only short-term data for only 249 sites nationwide. Only 204 of these sites have runoff quality data collected during this century, after 2000, and the median number of events per site is 16. Now, 16 is not a lot when you compare it to, 10 years of daily stream flow record. And even for a given site, if we compare that 16 monitored storm events, we can see that the average number of events per year ranges from about 17 in the average Southwest to 16 to 62 events in the humid Northwest. And the national average for the number of events per year is about, or I should say runoff generating events per year is about 40 nationwide. So to do the climate part of this analysis, we used the Federal Highway Coupled Model Intercomparison Project, or CMIP. It's a climate data processing tool to develop climate projections. What it does is you put in the information you want, and then it takes the average of all the available global climate change models, and it downscales those models to your area of interest. So this illustration shows the rough magnitude of the grid size for those climate models. You can see each grid cell is fairly huge, and so whenever you use this data, you want to downscale it to get a better idea of what might happen in your location of interest. So the CMIP tool it processes this data, it downscales it, and it gives you the relevant planning level statistics that you need at the local scale. So in our analysis, we used the global climate model projections for the centroid of southern New England. So we used the geographic centroid, but interesting enough, the population centroid and the National Bridge Inventory centroid for the number of bridges were in a similar area. So, so what we did was we used the data for these 4 climate grid squares that are centered on or near that centroid of the southern New England states, which I should mention are Connecticut, Rhode Island, and Massachusetts. And we compared those projections to the precipitation that would occur at all these NOAA precipitation stations within and adjacent to these states. So when we did our climate change analysis, we looked at 2, what they're known as representative concentration pathways, or RCPs. We used the 4.5 analysis and the 8.5 watts per square meter analysis. Now the RCP 8.5, as it's known, is known as the business as usual scenario, with continuing increases in emissions that match what has happened in the recent past. And we also use the RCP 4.5 scenario, which has a peak in about 2040 to 2050, followed by reductions in emissions. The RCP 4.5 scenario is considered most likely because 2040 to 2050 currently is considered to be peak oil. So kind of after that point, fossil fuels will become more and more expensive, and alternatives will be more advantageous in comparison to the increasing costs of fossil fuels. So when we did the temperature analysis, we found that monthly average temperature changes were expected to be 2 to 3 degrees for the RCP 4.5 and 4 to 5 degrees for the RCP 8.5 scenario. So what this graph shows is the monthly or annual average temperature in degrees Celsius on the vertical axis, and the month, January through December on the horizontal axis. So we can see here the current 1990 through 2019 is shown as the green squares, and then the RCP 8.5 and 4.5 are shown as the circles and triangles respectively. So as temperature changes, we may expect variations in hydrologic, water quality, and biological processes that may affect BMP treatment. Because these variables are not well quantified today, and because sediment removal is the primary treatment process for many BMPs, we just did a simple settling velocity analysis to get an idea of how, what's the importance of these temperature changes versus, and how they might affect BMP performance. So we know that changes in temperature affect the viscosity of water and therefore the settling velocity of sediment. We also know that the grain size of highway and urban runoff particulates can vary by orders of magnitude within and between storm events, and that the specific gravity of runoff sediment varies widely, by a factor of 2 to 4. In our simplified analysis, we found that uncertainties in the grain size and density dominate differences caused by temperature changes. So as we look on this graph, we see on the vertical axis, the suspended sediment settling rate in feet per hour from 0 to 70. And then on the horizontal axis, we have a bunch of different box plots. So for each grouping, we have the current scenario, the RCP 4.5 and the RCP 8.5 scenarios. And we are looking at, for each specific gravity, we're looking at average sediment size of 50 microns and 100 microns. And as you can see, for all these changes, we're looking at specific gravities of 1.5 and 2. Now, all these are well within what we see in available data. So if you compare the differences in the box plots, in each group of 3, which are the climate change differences, we can see that at the specific gravity of 1.5, that the change from 50 microns to 100 microns is a heck of a lot more than what we see the differences among the climate change scenarios. And similarly, for a specific gravity of 2, we see that the difference in that average grain size completely outweigh the differences that might be caused by the different climate scenarios. So what that tells us is for BMP treatment, all the uncertainties that we face in terms of what are the grain size distributions coming off our roadways and our urban runoff surfaces in terms of grain size and the specific gravity of particulates far outweigh what we may see in terms of changes in temperatures during in the near future. So once we did that analysis, we also looked at potential effects of precipitation volume changes. And we saw that the volume changes, the monthly average and annual average volume changes were about 7% for the RCP 4.5 and 9% for the RCP 8.5 scenario. So it's a factor of less than 1.1. So they're going to change, in general, less than 10%. So on the graph, we can see our monthly or annual average precipitation in inches. And I should mention here that these annual averages are the averages of the monthlies, not the sum of all the precipitation during the year averaged over a certain period. And again, on the horizontal axis, we have the months January through December. So what we see is there'll still be, seasonal variation in precipitation throughout the year. And there are, it looks like there's going to be about 7 to 10% changes in precipitation volumes over the year. So to look at what might happen as precipitation changes, we did what's known as a space for time analysis. So what we did was we used these spatial precipitation gradients to look at the potential climate changes. So if you look at the rain gauge statistics over southern New England, we can see that there's variations in the different statistics we use to simulate highway runoff. And the magnitude of those changes are greater than the potential magnitude of changes at the centroid of southern New England from now and into the future with these climate change scenarios. So the space for time analysis says we have data over space that shows a range of values, and we're going to use that change with space to predict or to estimate what may happen over time at that centroid location. So among the 45 sites, our annual runoff generating precipitation, mean event volumes, event durations, and the time between storm event centroids, which is known as delta, vary by a factor of about 1.71, 1.41, 1.77, and 1.48 respectively. So we can see that the variations in space across southern New England are much greater than the potential variations with time at our centroid location. So when we do this analysis, we will have a pretty good idea of the potential effect of climate change on water quality with respect to the other uncertainties we may face. So to do the water quality analysis, we used the Highway-Runoff database, HRDB, to get runoff quality data and statistics for southern New England. To characterize the conditions and do our simulations, we used highway runoff quality data from 19 monitoring sites in Massachusetts. To do our analysis, we selected 3 geometric mean concentrations. We picked the 15th percentile, the 85th percentile, and median of these geometric mean concentrations from the 19 sites to avoid atypical site. We didn't want an anomalous low site, an anomalous high site, so we chose this limited range within all 19 data. So we could see that there's small variation between the 15th and the median, but large variations between the median and the 85th percentile. So once we had our precipitation statistics we wanted to use and our water quality statistics we wanted to use, we then used the stochastic empirical loading and dilution model, SELDM, to simulate dilution factors and total phosphorus yields. So these are the results of our analysis. What you will see in the next couple of graphs is you will see the blue triangles, which is that high or 85th percentile geometric mean. So these are the yields calculated by using those statistics. And then you will see the median geometric means as the blue circles and the low or 15th percentile geometric means as the downward facing triangle. On each of these graphs, you'll see the horizontal axis is the variation in our precipitation, individual precipitation statistics. And on the vertical axis, you'll see total phosphorus yields in pounds per acre per year on the vertical axis. So as we go through the next couple graphs, you will see the exact same yields. They'll just be kind of rearranged in the order of the precipitation statistics. So what we found is that average annual yield was highly correlated to annual precipitation volume, which varies by a factor of 1.71 across these rain gauges in and around southern New England. So we see the correlation, which is Spearman Rho of 0.95 and a Pearson's R of 0.845. It shows that these values are strongly correlated to the annual precipitation volume. And that makes sense because, if you use the same concentration for every storm, multiply by the annual precipitation volume, you'd get the more precipitation, the more yield, because it's concentration time flow. However, SELDM doesn't use a constant concentration. It randomly varies the concentrations. So we're not getting quite the one-to-one relationship, but we're seeing that the relationship is very tight for the annual precipitation variable. However, I was a little bit surprised that the average annual yield was only weakly correlated to the average event volume, which varies by a factor of 1.41. So you can see in this case, the Spearman's Rho is 0.312 and the Pearson's R is only 0.316. So we're getting a lot more variation as we increase the average event volume in inches. So what's going on here is that the average event volume is not the only variable. We have the average event volume times the number of events gives you the annual precipitation volume. So we can see that this variable alone only accounts for about 30% of the variation from site to site. Now we see the average annual yield is moderately correlated to the event duration, which varies by a factor of 1.76. So we can see that the Spearman's Rho is 0.537 and the Pearson's R is about 0.597. So if you have the same volume and a longer event, the same average volume, times a longer event, you're going to tend to get more total precipitation during the year. So we could see this is a moderate correlation. And I guess I should have said, what we see in these patterns is that there's a little bit of increase with the different precipitation values that we're looking at, but we see the real variation occurring here is between the different percentiles of the geometric mean concentration. So there's not a lot of difference between the 15th and median concentration, but we can see that, if we use the 85th percentile geometric mean concentration, that the yield values are about 5 times the median values. So our water quality uncertainty is a lot larger than our precipitation statistics uncertainty. And we also see that the average annual yield was moderately but negatively correlated to the delta, which is the time between event midpoints. And these variables vary by a factor of 1.48. So what we see is as the average time between event midpoints increases, then you have fewer storms per year. So as one would expect, your phosphorus yield in pounds per acre per year would go down with fewer storm events. And again, even though we have a negative correlation here, we can see that the differences caused by the uncertainty in what water quality concentration we use is a lot bigger than the uncertainty in what precipitation statistic we use. And that's because the variation in concentrations is a lot bigger than the variations in precipitation. So finally, for all the simulations, the long-term average annual yields vary by a factor of about 1.55 for each geometric mean concentration, but the 85th percentile yield is 7.96 times the 15th percentile and 4.71 times the median yields. And I should also mention that the median yield is about 1.69 times the 15th percentile geometric mean concentration. So that difference at the bottom of the graph does not look huge, but it is about 1.69, which is larger than the variation in caused by variations in the precipitation statistics. So our takeaways from this study is that the hydrologic effects of climate change in this area is expected to be substantial. So it's important to mention that we're not saying that climate change is not going to be substantial. We're not minimizing it or denying that climate change is happening. We also found that our space for time analysis is useful because geographic variations in precipitation are greater than the climate change projections. So we can see what could happen over a larger range of values than our projected differences due to climate change. We see that many factors affect BMP performance, but our simple settling velocity analysis indicates that current uncertainties in runoff sediment properties are greater than projected temperature differences. We also see that uncertainties in selecting representative concentrations are about 5 times the variations in simulated precipitation statistics. So the bottom line there is we do need more water quality, more highway runoff quality data sets, and we need better ways to figure out which data set we may use at any given unmonitored sites. So Southern New England is fairly well behaved in comparison to some other parts of the country that we've seen, massive changes in climate over the last, 20 to 40 years, such as the Southwest. So in other areas, such as California, where they have a lot of highway runoff data, the uncertainty in water quality may not be as big as the uncertainty caused by the potential effects of climate change. So the paper that we published on this is open access. It's online now. It will be assigned a Transportation Research Record volume number and page range soon. When it's finally published, it should still be open access. The QR code here can hopefully help you find the article, and we have the digital object identifier on this slide as well. If you want more information, links to SELDM, the Highway Runoff Database, software data and reports are available on the SELDM webpage at www.usgs.gov/SELDM. This presentation will be uploaded to YouTube within a day or so for people who that might be interested, but who may not be able to make it today. All right, thank you very much for your time. I'll stop the recording and take any questions.